Hey everybody, gonna talk a bit about AT Tiny chips, which are some of my favorites. Uh, yeah, I'll get right to it. Quick intro, I'm Justin, as mentioned, not that Justin, different Justin. I'm mostly a programmer. I've been programming for a long time, relatively new to hardware. I've been through kind of a lot of this stack. I started back in Linux stuff and web development and mobile tools, and these days I do more systems and firmware type stuff. Um, like some of us here, I'm old enough to have used 8-bit computers, let alone 8-bit microcontrollers. But I got into hardware about 8 years ago. So I say this mostly to kind of orient as to where my expertise is. So I could probably pretty quickly get in over my head with questions, but feel free to ask anyway. I'm sure somebody here can answer. And yeah, I enjoy the elegance of efficient hardware hacks and part of the reason I'll get to it, but part of the reason I like AT Tiny chips is they're just small and relatively underpowered, but it's fun to do constrained things with them. So what are they? They were a series of chips. They are a series of chips by Atmel, acquired by Microchip in 2016. So they've been around a while. And the one in the picture here is one of the ones I'll talk the most about, the AT Tiny 85, which originally came out about 20 years ago, but is still in production. There's fewer features, fewer I/O pins, and less memory than other AVR chips you might be familiar with, like those behind a normal Arduino board, for example, until the most recent Arduino boards. And for the products that they've introduced until 2016, they were still producing them in this sort of form factor, which I like because they're breadboardable. The newer ones that have been released since 2016 are surface mount or smaller, packages. But like I said, these are still produced and available. There's a ton of these chips. And like I mentioned, I'm going to talk mostly about the AT Tiny 25, 45, 85, those three. You can go to this page on Wikipedia and it scrolls about 5 screen heights of this feature matrix. If you're really curious about all the history and all the stuff, it's a very Wikipedia chart. It's great, but like for our purposes, you're talking about these kind of clock speeds. It's kind of neat because you can do them without a crystal. They have internal capability for 1 to 8 megahertz. You can use an external crystal to drive them up to 20 megahertz. They also support phase lock loop, so you can do internally up to 16 megahertz. And the instruction set's relatively small. Most of the instructions are single cycle. The differences between these ones that I've mentioned, that I'm going to talk mostly about, the 25, 45, and 85, are in their memory capacities. So again, tiny, 2, 4, 8 kilobytes flash, and then we're talking bytes, hundreds of bytes of EEPROM or SRAM available. This is of course an apples to oranges comparison, but I was trying to find like an 8-bit computer of the era. Didn't really find one that fit in the same kind of frame of reference, but of course Nintendo, based on the 6502, is kind of in these same sorts of parameters, just for a little bit of perspective. Yeah, so peripherals, I've got the pinout on the bottom, if visual appeals more to you, but they're basically 4 ADCs available, analog digital converters. So you can hook up things like temperature sensors. You get 6 I/O lines, which is pretty good bang for your buck considering there's 8 pins. And then they can drive SPI and I2C peripherals, and I'll show some examples of that. They've got a little bit of a variance in operating voltage. Actually, I think that's wrong because they can be driven at 1.8 volts. The breadboard size operates at this voltage, so if you're using the smaller packages, you can drive them at 1.8. And the power consumption is also, as you might expect, tiny. They have a low power mode, which is just incredibly low power, and even active 300 microamps, pretty low draw. I'll talk more about that again later too. Yeah, so why? In my opinion, not every project needs an ESP32. They're fun to grab, they're powerful, but it's kind of fun, in my opinion, to use something that's a little more constrained or a little less overhead or a little less room to spare, and just to be frugal with stuff. And I'm sure you can find a range of prices. In general, just looking today at DigiKey and Mouser, we're talking $1 or $2 a piece for this sort of form factor. And like I said, I think they're fun, and I hope to show you that. So, dirty secret, much of what I've learned about AT Tinies and what has been exciting to me is largely based on this one website, which is a fantastic website by a guy named David Johnson Davies. If you've seen MicroLisp, ULisp around, which is a Lisp for microcontrollers of all different sizes, he's also the guy behind that. Part of what drew me into this site was every little project has a little photo like this, which I just love the compactness of it. I'm a sucker for through-hole technology and breadboard-sized project messing around, so I just love that things are done like this. The picture of this, the picture here is a pitch shifter, so you can send audio into this, click the up button or the down button, and shift the pitch on the fly. So it goes to show sort of a surprising amount of functionality that can be squeezed out of these little chips. So here's a couple other projects just to kind of highlight. I brought some demos beyond these, but I just wanted to mention these and kind of show the range of things that he has highlighted on this site, and that I think exemplify some of the best things you can do with the AT Tiny chips. The top left one is a MIDI player. That's a little red LED that will actually flash if there's a parsing error in the MIDI. The top right one is a widget dashboard, and he's got a little library that he's written that'll drive a display with a variety of widgets you can hook up to sensors. The bottom left one is just a TFT graphics library, and he's drawn some curves in it there. And he's I'll get to display a little bit more later, and then the pitch shifter that I mentioned in the previous slide on the bottom right. So how do you program these things? If you're like me, so I got into these chips about 5-6 years ago, and my experience in programming chips had just been limited to dev boards and things like Arduinos, where it's got a USB controller on the board, you plug it into your computer, and you flash over your program, whether that's through Arduino IDE or Platform IO or whatever. So this was kind of a neat way for me, and part of the reason I enjoy these and have a soft spot in my heart for them is it was a neat way to get into programming chips that are literally, they can fit on the tip of your finger. And so a nice way to get started with this is a project called AT Tiny Core. So whenever somebody ports Arduino IDE capability to a chip set, they call it the core for that chip. And so he wrote AT Tiny Core, which allows you to use Arduino stuff you may already be familiar with, like setup and the loop functions that are built in, and program these little chips. So it's a nice way to get started if you don't want to just jump right in as straight C or C++. And then I included these fritzing diagrams. If you're not familiar with fritzing, it's just a kind of a visual schematic. I find it nicer if you just want to lay something out quick on a breadboard. You don't have to do both steps of parsing the schematic and figuring out how to lay out your stuff. You can just follow the picture. So the one on the bottom left is probably the simplest way you could do this, and I'll talk some more in a second about why there's an Arduino, the blue Arduino, involved in this situation. But you can see the AT Tiny here on the breadboard. And then this is sort of the minimal situation by which you can use an Arduino to program the code on the chip. And again, I'll talk more about that in a second. And then a little more involved, fancier version is something like this, where one of the lights will be pulsing as a heartbeat to let you know it's ready to go. And then you've got a light flashing as it's flashing the firmware over to the chip, and another one if there's an error or a problem. Same idea though, the AT Tiny just goes on the breadboard here, you program it, then you put it into your other breadboard that has your project. What I tend to use is a programming shield, and so I've got the one in the larger top picture there. I got it off Tindy for like 20 bucks. It's meant to fit over an Arduino Uno, so here I have mine. This is a nice little SparkFun Arduino Uno with breadboard thing that I have, which I find really nice. So the shield just goes over top. You drop the chip into the thing, clamp it down, and then you can program through the Arduino, program your chip, pop it out, and then I put it over on the breadboard for the circuit I'm actually working on. There's simpler versions. This one's kind of fancy. It's got, you can see the 3 lights up here, sort of what I just talked about in the last slide. It's also got a yellow LED hooked up to pin 3 on the Tiny. So if you want to like start with a blink sketch on the Tiny chip and make sure your programming setup is working, you don't even have to take the chip off of the programmer. Once you flash it, the yellow light starts flashing, driven by the Tiny chip. And then the one on the bottom right is a much simpler version. It's just drop the chip in. No lights, no switches, no toggles, no. It can only take an 8-pin, that sort of situation. Yeah, so I like those because it's a neat way to, but like I mentioned on the previous slide, you could just get going with an Arduino you might have and a breadboard and jumper wires. Yeah, so I mentioned we're using the Arduino in a lot of cases, or it's a simple way to program these chips. Included in the Arduino IDE in the examples, my mouse pointer go? Yeah, that's right. Included in the examples, way at the bottom is this thing called Arduino ISP, which is a sketch that you put on your Arduino, and that makes it the thing that can drive a shield like this, or the schematic in the earlier slide to program the chip. And so once you've put this sketch on your Arduino and you've got your Arduino connected to your computer, the sketch that you upload and you select ATtiny as the chip just transparently goes through the Arduino onto the chip. And that's kind of the workflow. I made a diagram about that. Yeah, the basic idea is that it goes into the breadboard or the socket on top of your Arduino, and you are then using this thing transparently to just program the chip on your development cycle, your loop. Yeah, so I made a once I got going with this, I made a project. Like I said, I got into this about 5 or 6 years ago. So towards the end of 2020, this was actually my first KiCad project too. I'd never done my own PCB. And so I made this little tree ornament. It's got an ATtiny 25, so it's the smallest one with 2K, a flash, and then a couple transistors, a little battery, a piezo, and a button. And I'll talk more about how the button is working because you might notice there's not a slide switch. But when you, I don't know if you can quite hear it, but it plays Jingle Bells. And it does that on loop until you hit the button again. And I'll talk about how that toggle is happening and there's no slide switch and it's actually conservative of the battery. But yeah, this was, once I got going, I was like, okay, great. Now I can put this chip in something. And in this case, I could have soldered the chip. I just have it in a socket so I can pull it out and do whatever else with it. But that, so I started with a prototype using this very same board, which is a complete mess because it's got 5 red LEDs, 5 green LEDs, and a yellow LED, and then all the associated resistors. Yeah, but I wanted to test the whole thing. I did put a slide switch in this situation and a little battery, and I just wanted, I was kind of paranoid about the whole thing because I was ordering my first PCBs. And because I prototyped it right, it worked the first time. But you could see using the ATtiny 25, I'm pretty much maxing out what can be done. This is about a 70 line of code Arduino sketch. And that includes all the notes to be played and the little power management loop and that sort of stuff. But it's using 94% of the flash and then pretty close to all the dynamic memory. But yeah, that was my prototype of it. And then that kind of led me to, okay, cool, maybe other people started telling me they wanted this thing. So I ended up selling assembled ones, which I'm not going to do that again. That was a lot of work for the overheads involved. But more people were interested in the kits anyway. So I haven't sold them in a while, but I kind of made it year agnostic and then started selling them on Tindy, which was a lot of fun. And people enjoyed it because it's sort of, I don't know, a lot of people like me, I think, enjoy through-hole soldering. It's just a fun project to make, especially maybe if you're new to soldering or with your kids or something like that. I've open sourced the sketch and the schematic and all the stuff too. I'll link all these things in Discord, but this has been out for a long time. And so it's on my GitHub as well. And I blogged about it, so I've got a lot more detail about sort of the stuff I've talked about, the programming circuit and things like that. One of the things I picked up from the Technobloggy site that I really enjoyed was this just clever way of cycling or toggling the chips to go into the low power state using their reset pin. And so this is more or less what I've built into my tree ornament thing, so that you push the button once and it wakes up the chip and loops its sketch or its firmware. You press it again, it goes into its sleep state, which you might remember was 0.1 microamps of current draw. So effectively, like I've made a couple of these for friends and they leave the battery in year to year and it's mostly been okay. Like they can pull it out a year later, hang it on the tree and hit the button and it works. So it's kind of neat considering that technically the Arduino is running for that year. Yeah, so I'm gonna do, if the demo gods are with us, I'll do a couple demos. I'll just show an overview, and if I can get somebody maybe to hold my camera I'll show you some stuff live. But a couple that I made um, and again, I'm stealing a lot of content here from technoblogE.com. I really have an appreciation, like I said, for the photography because his looks so good and mine. You can see how poor my soldering is on my display and how dirty my breadboards are and how nicked up my jumper cables are and everything. But this is one I made this afternoon, which is here, and it's an AT Tiny 25 driving a little SPY display. And if you pull the display up, this is kind of what I had to jam in there behind it to make it work. And I'll show that in a second. And I also brought button cell batteries and a battery holder so they can, unlike this photo where I've got power and ground going out the side, I could just run them completely in the palm of your hand. And then the other one, I'm going to drive this speaker with another one. And it's a 4-voice MIDI synthesizer and small MIDI language parser. And it plays a polyphonic tune using this button battery and this circuit here through the speaker. So yeah, let me do the demos real quick, and then we can do questions and things. So let me see if this works. I think. Oops, that's not what I want. Let's see if this works. That's pretty good. Yeah, cool. Thanks, Reed. I guess you've already seen the tree, but we'll just make sure this is working here. So, oh, I'm totally disoriented. Here we go. Yeah, so that's what that does. And then it just loops. So a future version of this might, I don't know, do motion sensing or something, because it's either like hanging on your tree, not doing anything, or just cycling indefinitely. Yeah, so this other one here, see if I can get this wedged together. Actually, I'll do well, let's do this one first. Let me think for a minute here. Really kind of shoehorning this in, but should work. There we go. Better battery of my two. Get your power up. Of course, that's not going to work for me. I mean, I could also show these after the fact. Let's try this. There it goes. Oops. Yeah. Oh, there we go. Yeah, which is kind of fun. This one doesn't do anything in particular, but I just thought it was nice to show off some of the graphics and how little circuitry is actually needed to drive a display like this. And then the other one, we'll get a little bit of wiring here.
What frame rate do you think the display at?
Good question. I don't know off the top of my head. One thing that you will run into is you have not enough RAM to do a frame buffer or anything. So there are some useful projects on that guy's site around displays that support reading back off of them again. So you can read the pixels on the screen and not have to store them in RAM, and then you can start to do some better, more efficient graphics with that. I don't know on the frame rate offhand. I haven't really driven that much animation-wise. Give me one sec here. So this is positive. This one's negative. Which is going to be this guy. All right. Put the battery in. Hopefully this will pick up too. Oh. Oh, my clips aren't on. They attach to my magnet. That's what's going on. Let's start this up. In transit. Yeah, right? Yeah. I don't want to be touching it when I'm doing that. Yeah, here we go. So clamp the things. All right. Yeah, so 4-voice sound, which yeah, it's pretty impressive. And again, these are both 85s. Actually don't remember what the overhead was like. You could probably do them on a 25 or 45. And I should mention, let's turn that on. I'll let these run afterwards. I should mention there are other form factors, not just the 8-pin chips. There are some longer ones, like the one that was shown on that Wikipedia page that I showed. They have more I/O pins and more capacity. And there's some that are quite a bit faster. Like I mentioned, these chips came out in 2005, the 25, the 45, and the 85. But I like them just because they're fun 8-bit chips that are fun to play with. Yeah, that's kind of all I've got. I'm open for questions or comments or experience anybody else has. Thank you.
Got a question.
Yeah, Danny.
So does it have a digital to analog converter, or how are you able to drive that speaker just from the chip itself?
Yeah, I'm probably in over my head. I knew it at one point, and then I just built it again today and do not remember how it all comes together. But roughly, let's see if I can.
I mean, I guess my question is, there's no other chips on there that you're using to
No.
amplify the signal. Okay.
No, yeah, you can see on this one, we've got a small cap here, pretty big one. This is a 220 microfarad here, and then there's nothing sneaky going on underneath the battery thing. It's just connecting the pins.
That's cool.
Yeah, so I did find I had this is an 8-ohm speaker. I found, I had some little project ones, and I was not getting anything out of that. So I was like, well, let me pull out my Beat to Hell giant magnet speaker and see if it works. And that's the first thing I got decent sound out of. So yeah, it's not being amplified. I really can't speak to the specifics of how it's working, but I'll tell you one thing. In preparing this again today, I wanted to remember and want to go back and re-remember so I can explain it better. But yeah,
Cool.
I wasn't going to cover that today. So, yeah. But yeah, no other chips, nothing else going on in this.
What is that big block?
Yeah, that guy's the 220 microfarad capacitor. So you can see here the third pin down. That's the one that the audio is coming out of. So you trace that out into the cap there, and then where it's coming out is the same row, the top row, where I've got the white wire coming out. So that's the positive, or the one side of the speaker, and then the ground. This is just bringing ground up to the black one to go on the other end of the speaker. So the waveform that's being synthesized by the Tiny is going straight into that speaker by way of the cap. The cap is for filtering. It's related to frequency filtering, so we don't get a whine. That's what's going on there. It's not amplifying or doing anything like that. As is the Tiny cap here is related to. That's between 5 volts or 3.5 volts in this case, and ground. Again, filtering to make a better sound. Perhaps someone else knows more about that off the top of their head, but that's all I've got as far as the. Yeah, cool, awesome. Yeah, thanks. Questions or thoughts? Yeah, it's kind of fun. It's yeah, obviously the speaker could be louder, but it's pretty neat that it's clear. Yeah, it's nice. Yeah, it's pretty impressive. So
Question.
yeah.
The Arduino boards that the shields.
Mm-hmm.
Do they make those for the surface mount chips as well?
I believe they do. I've seen ones that are more related to like clamping on the top of the chip.
Sure.
So you'll set the chip and like clamp a thing in, because they obviously don't go into any holes because they're
Pressure in the contact.
Yeah. There are a variety of them on Tindy, for example. And yeah, I don't do a lot of surface mount projects myself. I tend to do stuff like this, and
Limited stop.
yeah, well, yeah, right.
Oh.
Yeah. So yeah. Other questions, thoughts?
Question about the display.
Yeah.
So how much of the flash memory for that little project is code? How much is the graphics?
Yeah. So in the case, I should have mentioned, one of the things that I learned the most from following that guy's AT Tiny projects was how relatively straightforward it is to write a display driver for these types of displays. And so there's no, like I mentioned before, Danny, there's no frame buffer stuff going on. So it is, it's doing like a setup routine, which is usually like toggling a pin, hitting a reset. In the case of the, let's see, let me put it back together here. In the case of this circuit, it's pulling, this is the backlight pin, so it's pulling that high to keep the backlight on when it's got power applied. But you've got the control, the clock select, so the clock select will toggle when it's like, I'm writing to the display now. The control is for going back and forth between data or commands. That's why it's called DC. So short version, what he's written for a lot of his graphics libraries are like on the order of a dozen, 2 dozen, 3 dozen C commands that are manually toggling these pins to, and it's at certain points waiting a millisecond or less where needed to take the display through the routine that it needs both to set up, and then it'll toggle DC to data and write integer values 4 pixels on the fly. So it's doing it all on the fly. So in the case of when this was powered up, it drew that once, and then it's just going into like a wait loop. At that point, there's not like a frame refresh going on. You could write that sort of thing, but that's why with such limited RAM on these kind of chips, that's why it's useful to have this display is not, but screensaver, sorry. That's why it's useful to have a display where you can read the pixel values back out via one of the pins, because then you don't have to have stored that anywhere, and you could say if this, do something, or if not, or XOR it, or whatever you need to do to make graphics animate or things like that. So
I guess I'm most curious about, I saw there were like numbers and like some text on the display. Did you do any tricks to like kind of compress that to save as much space as possible?
yeah, that's so his libraries for that sort of thing do that. He stores the fonts as bitmaps, so each one I believe is a byte, and it's literally like, you can, if you were to spell out the hex value of it, you could see the on or off value of 6 by 8 pixels for a character, for example, that sort of thing. So it's inherent in. I could pull up the sketches actually to show you. That might be more enlightening. So if we do, for example, the TFT is the one that I was showing with the display. Sure. This is roughly, like, this is all inclusive here. So here is the font. This is the bitmap font all the way down. So that's that data. And each of these is, each line is a character, I believe is how it's set up. So 96 characters. And then, there's different byte values for doing these various commands that I was mentioning for the display. So that's all included in here. This stuff is related to driving the display, clearing the display, which is a series of commands. You send like 5 or 6 bytes to the display and it'll completely wipe it, that sort of thing. And then here's the line drawing primitive, for example. So it's all inclusive in this sketch, filling a rectangle, plotting one of those characters looks something like this. So it's really enlightening to see what goes on behind a bitmap display and how simple it really can be. And then here's, the setup and the loop of the Arduino. So that's it. That's the whole sketch for that static bar chart display, including the font, all the graphics, all the line drawing and primitives. And so he's got some other, I don't know if I'm online right now, but he's got a whole set of libraries for doing more accelerated things like 3D drawing and doing the transformations of that. Those don't tend to run as well on the tiny chips, just because they're limited processing power. But I mean, if I haven't indicated already, I'm a huge fanboy. I highly recommend that guy's site because there's just so much to learn there about squeezing performance out of this type of chip and just thinking frugally about display drivers and 8-bit audio synthesis and things like that. So, yeah, any other questions? Thoughts?
Could you repeat the domain name for this
Yeah.
site?
Yeah. Yeah, totally. Here we go. Just like technology, sort of, but technobloggy.com. And yeah, just fantastic. He's got dozens and dozens, and he categorizes them by graphics, sound. He's a big fan of Lisp, clearly having written a Lisp dialect for microcontrollers. So there's small computers you can do with a bit beefier AT Tiny. You could build on a breadboard this size with a display like this and plug in a PS2 keyboard, if anybody's familiar with that era of technology, and bring power and a PS2 keyboard into this and program in a Lisp environment on a little bit beefier Tiny chip. So yeah, a lot of great projects. If you take nothing away from my talk, go to his site.
Just something I was gonna suggest, if you were to ever revisit your, ornament.
Yeah.
It looked like you were maybe using just 2 I/O pins.
Yes.
Yeah.
Maybe yes, I am, because I think I tie the yellow, the top one to high, so it's always on, and then I've got 2 I/O pins going through.
Well, if you use more I/O pins, but you only need like 4 or 5, you can use Charlie plexing.
Yeah.
You could have.
You could do more than just alternate red green. Yeah, that's a good idea. I of course have to redo the board, but yeah. Yeah.
I think somebody got like an 85 to do it something like WS2812.
Wow. Yeah.
Not many, or
Yeah. Yeah, for this I'm using it's still on? Yeah. I'm using, let's see, I've got IO or reset goes for this. I'm using IO for the sound, 1 IO each for the red and green light by way of these transistors. And then I think that the yellow is just tied high when the circuit's running. And I think that's it. So I'm not even using all the, this is a 25 because it was near maxing out the flash capacity, but I'm not even using all the IO pins on this thing. So, yeah, it's the back a little bit more, give a sense. That was a fun routing project to try to figure out how to do this. It taught me a lot because I wanted some symmetry to it too, and it was fun to do. Yeah, thanks. And again, if you wanna find any more like the stuff that I mentioned here about this project in particular, I have it on GitHub and a blog post on my site, which, oops, here, justinmiller.io. So you can find it there pretty quickly. Yeah, thanks.